Can you all hear me? Yes, great. Hi everybody. Welcome to the last event of the Elastic project. We have a hybrid event this morning, so we have people in the room and people online. So just for the people that are online, you'll have the ability to ask questions during the event. We'll take those questions at the very end. First of all, I'd like to thank the Metropolitan City of Florence for hosting us in this amazing place this morning. I'm sure we'll have a great event. So, just to start, I'd like to we'll have the program here on screen. We'll try to stay to the time allocated so that we have enough discussions and questions at the end. So. If I ask you to stay on time, then please bear with me. Just to start, the welcoming notes will be given by Eduardo Quinones from Barcelona Supercomputing, and I wish everybody a great event. Thank you.
Okay, so thank you very much for attending this meeting, those that are here and those that are online. So I'm going to provide a quick overview of what is the project Elastic. So the first thing, let's just provide very generic information about a project. So Elastic is a European project, and Elastic stands for a software architecture for extreme-scale big data analytics in fog computing ecosystems. It is a project that started 3 years ago. In fact, the project finishes today. Today is the last day of a project. And it is composed by 8 partners. So what is the project about? So the project is about how we can extract knowledge, valuable knowledge from the data, from the massive amount of data that is generated from a city. So if we have this picture, there is not much we can say about it. We can see a person that is crossing. But if from this data we apply a set of data analytics, for example, to detect the people, to track them, to extract the semantic information, and so understand that there is a car that is approaching, that there is a pedestrian that is crossing. And more important, if we fuse this information with other sources, like semaphores, we can then understand that this is a dangerous situation. And this information is very valuable. It's knowledge that then the city can use to inform a car that there is a pedestrian crossing. A fundamental element is that this information needs to be provided in real time. This means that the end-to-end response time of these analytics needs to be provided in a given time value. If we provide this information 10 seconds, 5 seconds after it happens, this information is useless. Okay? But if we provide this in less than half a second, maybe we can use this information to be transmitted to the relevant actors. Moreover, this information is also very valuable, not only for real time, but also for storing this information and, for example, understanding how many times people is crossing in red. And this is a very valuable information that can be used to implement better mobility policies. And just to show you that I'm not lying, there is the guy that was crossing while the traffic light was red. But of course, the challenge is not analyzing this data, because in fact, there are very good data analytics methods that can do this. The challenge is being able to manage all the data, all the massive data that a city is generating every day, every minute, every second, because we don't have a single camera. We have many cameras. We have also information coming from other public transportation. We have information coming from other sensors. And so here the question is, first, how we facilitate the people to develop their analytics so they can really extract the knowledge that is needed from all these data or all these data sources. And also, how we can map them to the computing resources available in a city, because at the end we need the computing resource, the communication resource in order to implement this type of analytics. So this is exactly what is the project about. The project is about how to deal with all this complexity, how we can deal with the massive data sources that can be processed in an heterogeneous computing environment composed of edge resources, IoT resources, cloud resources, and how we can transmit all this data through an heterogeneous network infrastructure. And this is exactly what is the project about. How we can address all this complexity. And these are the key objectives of the projects. How we can address this complexity to first facilitate the development of these complex data analytics workflows independently of the underlying platform. And this is a key to allow the programmers to develop their functionalities so they can extract this knowledge I was talking before. If we provide access in an easy way to this, what we call the compute continuum, this infrastructure composed of IoT, edge, cloud resources, this will facilitate, this will open a new opportunity of implementing data analytics at different levels. So we can implement analytics at the edge, real time is provided, or we can provide analytics on the cloud, in which we have highly computational capabilities. And something that is very important for the Elastic project, that is, all this needs to be fulfilled, all this needs to fulfill the requirements imposed by the domain, real-time requirements, energy-efficient requirements, privacy, security, etc., etc. What we have done in a project in order to address this, we have implemented what we call a software architecture, gathering a set of technologies that makes this possible. Those technologies independently were not able to provide these features, but by gluing them together, we have been able to provide these functionalities. And how we have, and in order to prove it, to prove that that the capabilities of the software architecture, we have implemented this in 3 smart mobility use cases, addressing the challenges towards autonomous vehicles, developing analytics in order to provide smarter and safety mobility, and also enhancing the maintenance services of a tramway. And that's all from my side. I really hope that you enjoy this event. And now I think it's time for the use cases to present. Thank you.
Thank you very much, Edu. I didn't present myself, I realize, so I'll be your moderator this morning. And so my name is Marc-Élian Bégin. I'm the CEO and co-founder of 6 Squared, one of the partners in the project. So after this great intro, our first session is going to be intelligent tools for smart transportation. So I'd like to welcome on stage Gianluca Mondo and Vincenzo Di Massa from Thales Italia, as well as Jürgen Asfalg and Claudio Ravaglia, from Jest, and of course Jürgen is our host Where's our host from the metropolitan city of Florence? Are you? Okay, that's great. No, I'm not. So please take a seat, and I'll give you the mic.
Okay. Okay, good morning. I'm Gianluca Mandò, Innovation and Technology Manager in Thales Italy. Thales Italy in this project has an important role in managing and coordinating all the activities relevant to the use cases, Work Package 1. In particular, in the role of Thales here was to implement important steps, important pillar of our strategy in the autonomous tram solution. In fact, it was the opportunity. Okay. It was the opportunity for us to develop two important systems that are the basis of the autonomous tram. The first one is the positioning solution, what we call NGAP, Next Generation Autonomous Positioning. It is the system that allows the tram to understand, to be aware of what is the position along the tramway line, independently from any system that is installed along the line on the ground. So our ambition here was to be really autonomous in calculating the position of the tram, and the challenge behind is starting from elastic to certify this solution at the maximum integrity level for railway. So it will be at the end this product a SIL4 product because this will allow us to remove safety elements on the ground, tram detectors, because the tram itself will calculate its position and will detect its position along the line and will send it to the signaling system. Okay, our NGAP is based is collecting data from several sensors, in particular radar, NIMU, Inertial Measurement Unit, and GNSS satellite system. Then we have designed a specific data fusion, sensor fusion algorithm that is able to collect all this data and to fuse them to calculate the position and the speed in a reliable way for the tram. So these are our sensors, just to give you a concrete view of our system. That is the continental radar. We have an inertial measurement unit, and in the lower part of the slide, and a GPS GNSS receiver in the middle. So we used commercial sensors coming from the automotive market, and we integrated it for a different application, the tramway application. So these are the performance that we achieved. You can see here that we are able to achieve an accuracy in position below 1 meter. We are around 60 centimeters really, all along the line. There are other technical parameters that you can see here in the table, but are really relevant for calculating the integrity and the reliability of the system. In particular, the protection level is an element that will allow us to achieve the maximum level of certification in terms of railway certification. Then we are able to calculate the speed accuracy. You can see below 1 kilometer per hour. I repeat, all without using any element installed along the line. These are the trams that we have equipped with our solution. 3 trams are running in Florence, equipped with Thales sensor fusion algorithm with a high-performance computing on board, on the edge, because the tram in the elastic architecture is on the edge. We need the real time for calculating the position. So the algorithm is running real time on board on the edge, but is also providing this information, the outputs for other application in the cloud. So completely leveraging on the elastic architecture. You can see here other picture representing the installation. We performed several installation with engineering vehicle also, the vehicle in the middle, not only before arriving to install the sensor in the tram. You can see in the middle of the tram, quite well industrialized, the LiDAR and the radar. So what I could consider a quite final industrialization of the solution in terms of this integration in the design of the vehicle. We developed a tool also for evaluating our performances. As an example, we have designed and implemented and gap diagnostic and simulation tool. So we collected the data from the tram in real time. We send the data in our premises in Florence, and we can run the algorithm in our premises for calculating the performance and for evaluating the results. You can see here, in fact, in the next slide, a video. I hope it's running, yes. This is the HMI of our tool that we use for development, for engineering activities. The video is synchronized with the data coming from the sensor. In the lower part of the slide, in the small yellow circle, you can see the tram moving along the line. Just a quick explanation. On the right part of the slide, you can see the speed calculated by the GPS, very reliable. GPS is reliable for speed. And by the radar, our radar. You can see on the left the three accelerations calculated by the IMU, and you can see some strange behavior when you face a turn, a curve. This is important for us for evaluating the performance of the sensors and of the algorithm and the solution overall. The two last picture here in the lower part are the picture that can allow us to arrive to the certification, because in the blue line, you see the error that the algorithm is achieving, comparing the output of the algorithm with a ground truth. And if this blue line remain between the red lines, you can be sure that you are integral and you can achieve a high level of reliability up to SIL4. SIL4 for railway is the maximum level of safety. And we evaluate the performance with this diagram, usually used in the avionics. That is the Stanford diagram. The important thing to be certified is that the error stay within the white triangle. If you stay over there, you can achieve the level of certification that you need for railway to be autonomous in the future without any driver. Now I leave the floor to my colleague, Vincenzo Di Massa. Yes, there is some other slide relevant to giving you how our solution is calculating, how well calculating the speed of the tram. Okay, now Vincenzo will speak to you about the advanced driver assistance system, collision avoidance system, also called in our solution. Okay, I give the floor to Vincenzo.
Thank you, Gianluca. Thank you, everybody. And so I will talk to you about this obstacle detection system and driver assistance system. This part has been implemented in the Elastic project. Okay. This part has been implemented in the Elastic project with the purpose of providing data to the city about what the trams, while driving, see in front of them. How do we perform this detection? Basically, we installed some sensors on the on the tram itself, and we transform trams into moving computers on which several algorithms are running. Here you can see a very raw architectural diagram of the system. No problem. Very raw architectural diagram of the system, and basically it's a pipeline from left to right. So sensor data arrives, objects are detected, then from different sensors and different object detections, the information is glued together, is merged, or as we say, is fused. So we perform a sensor fusion technique, and at the end, after fusing and filtering the data, we get the detections, and we decide what to do, if we have to warn the driver, because the system is an autonomous driving assistant system. So if we have to warn the driver or not. So we are using sensors, like in the previous presentation from Gianluca. I will show you quickly that we are using a radar, a LiDAR, and cameras. This is, of course, nothing special about this. A LiDAR, basically, if somebody doesn't know, it's a sensor that emits blades of laser light that scan and sense the distance of what is in front of the sensor rotating. So we have these rotating blades that detect the distance of objects. And radar and camera are sensors that everybody knows about. So in order to take the data from sensors and detect objects, we need object detectors, and we need some technology, and then we need some technology for the sensor fusion part. So what are we using? We are using, of course, neural network for the cameras. We are using Kalman filtering, so optimal filter tiering for the sensor fusion, and we are using a lot of important algorithms that allows us to reach the performance level that are needed for what we will do in our roadmap in the future to certify this system as well to be a component of our autonomous roadmap. Now is the interesting part of the presentation, the demo of the system through a video. So here you see the system that we have implemented to understand what is going on inside of the sensor and inside of the algorithm. This system basically is showing you a recorded run of the tram through the city. On the top left, you can see the picture from the camera. On the right, you can see the output of the 3D space sensor detection and sensor raw data. So what you have here is the LiDAR data, is the lines that represent the objects in the scene. You have the blue boxes, that is the result of the object detector on the LiDAR data. Then you have small blue dots. I don't know if they are clearly visible in there, but there are many on the top left corner of the scene. These are the radar raw data. So, and you have other dots here, like this yellow dot, that are the output of our sensor fusion algorithm. So the part that fuses radar and LiDAR together. We are not using camera here because it would be too much information, and we are not filtering out in this representation the noise, because the noise here, so all these lines that are not objects, help the human people to understand what is the correspondence between this picture on the right and the picture on the left. So I will start the video. Please focus when the tram stops in a few seconds on what is happening on the left behind the poles. There are some infrastructure poles, and there is a woman there. In that part, you will see clearly why we are using different sensors, because at the beginning, the radar will have low accuracy. You will see a dot from the radar very far away from the woman that is crossing the street, and the LiDAR will help the detection. Then, in the other way around, the situation changes, because the LiDAR will have difficulties to distinguish between the woman that is continuing walking and the pole, but the LiDAR doesn't have this problem in that part. So you will see that the two sensors are actually helping each other. So I start the video. no, sorry. I start the video, okay. So the tram stops, and on the left you will see the woman. You see the woman is approaching, is the dot that is, the red dot that is happening there. Now you have the LiDAR detection. Before was not LiDAR detection, just the radar was detecting the woman. Now the woman will go close to this pole, and his blue blob will be fused with by mistake of the sensor with the pole, but the system is still tracking the woman. Now on the right you will see a bicycle. A bicycle will appear here on the right, and the two sensors will cooperate even in this case, because at the beginning both of them will see the object, but when the bicycle drives far away from the system, the LiDAR will, here is the bicycle, the LiDAR will stop seeing the bicycle. But still we are tracking because the radar is continuing until we reach the limit of our system that is at this moment is fixed to 40 meters for demo purposes. So this is another part that is interesting about this presentation, and is the crossing of several people. Here we see that the system is capable of tracking the people that is crossing, and is tracking the people even after they go out of the camera view. There is a couple that has just went out of the view on the right side. A few seconds more, and we will reach another station where we will see many people crossing in front of the train. And we will see that the system is capable of tracking individual objects even when they overlap with each other, while walk in different directions. And we are still, you see, there is many people walking, and we track them quite accurately, even if sometimes one of the sensors have trouble, because due to occlusions and these kind of problems, it's not always well possible to see the sensor measure output. So what is the final result? This is the final result. So when people is walking in front of the tram, this is what the driver can see. So a lot of work to just make a beep, okay, for the driver. But what is important for the Elastic project is that the data that is behind the scene running is flowing inside of the Elastic system, and take part into the decisions that all the Elastic project is doing about the city, smart city, I would say, infrastructure. So I give the floor to my colleague.
Thank you. Okay, so I'm Elisabetta Furlan. I speak on behalf of Jürgen from the Metropolitan City of Florence, and I will present to you the second use case. Okay, I guess we have to skip a little bit. Skip. Okay, I thought they were just put all in queue. And here we go. So this is the use case that we are presenting. As Eduardo was saying in the introduction, we studied the interaction among different transportation modes, in particular public and private transportation modes, in the view of a smart city framework, trying to base ourselves on the fog architecture provided by Elastic. So why is interaction so important to us? Well, in an urban context, we have many times a situation like this. So we focused in particular on the tramway, the T1 line. And there are many places where the tramway is going to cross also car traffic, other vehicles traffic, in intersections where we will also have pedestrians on the road. And all these kind of interactions on the one side might pose a hazard. There might be someone skipping a red light, just passing through both a car and a pedestrian. And on the other also gives issues about optimization of the traffic, both for the private and the public transportation. So what I mean by performance or optimization is a situation like this. We know that typically public transportation is given priority. So if there is an intersection and a tram is coming, the red light is going to come up for the cars, so they stop and the tram can just pass by. But there might be bad situations, say where the first tram comes and then there is another one approaching the intersection. So the cars won't get a red light straight away. They will have to wait for a gap time where no tram is actually crossing the road, but they're just waiting for the next one to come, and then traffic might be piling up. So it is important to monitor these kind of situations, make sure they don't happen too often, and if they do, try to prevent them, slow down the trams, make them stop a little bit longer at the stop, so that if they need to occupy the intersection at the same time, they really need to be there at the same time, and we don't slow down also the private traffic. Another very important issue coming from these interactions regards safety. So there might be some flaw in the design of the intersection where, for example, the visibility is pretty low. Here there's a tree on the way, and just someone might not see the tram coming. So in principle, they will have at least an orange traffic light, but they might say, okay, I'm gonna make it. And then sometimes they don't. So of course this is going to pose a risk and is also going to affect the performance of the transportation system, and we want to avoid a situation like this. So we want here to have some kind of device in place that is going to give some feedback to the driver and tell him that there is a danger coming ahead. And the same thing also for the pedestrians crossing. It happens very often, there is a red light and the pedestrian just goes anyway. And here it is important both for the driver to know that this situation is coming up, as we just saw earlier, but also to understand why this kind of behaviors come up. So we want to collect the data, store them, and then analyze them to find some patterns and understand if, I don't know, maybe the pedestrians just want to run to the bus, but there is no green light for them, so they just decide to cross anyway, or if they think, okay, no car is going to come anyway because there is the tram coming, and so I'll just go. So this was the general setup, the idea of what we were aiming at. Now I'm going to show a little bit how we put it in practice. So once we had a clear vision of what we wanted to get, we had to study how we could really implement it. So go to the place and see how we could put all the devices to get up the data, how to optimize their distribution so that we didn't have too many of them, but still we could collect a significant amount of information. And we came up with this sort of design where we had a few different components. We have monitoring components, so we have, for example, cameras that are telling us what the pedestrians, the cars, the trams are going to do. We also have a monitoring system for the traffic lights, which tell us when it's red, when it's green. We also collect data from the tramway, and then there is a part of edge computing which is going to process all this data that are collected locally, and if there is any risk arising from the situation, then there is an actuator which is going to transmit some kind of warning advice to very specific devices which are put on board of the car. So this is the part which is performed at the edge, and then there is a part that goes into the cloud. So there is a system of connections among all the devices local, and then from the devices to the central cloud, where then the batch analysis is going to be performed. So just to be a little bit more specific, first there was a study of a situation like this. So on the top you see the intersection we wanted to study, and we could decide to put the cameras, say like on the left or the right. Of course you need to decide the position, the angle, how tall they need to be, how many you need to have. And this is the final realization on the bottom. So you want them to capture as many elements as possible. And these are the 3 places along the tramway where the cameras were put together with all the other monitoring, recording and transmitting devices. And then there is a fiber optic connection among all these sites and then to the central cloud to transmit the data. And of course, infrastructure was already present. There were already traffic lights. So we had to put in place some ideas for how to monitor the status of the traffic light without impacting their security, say their certificate. So we had to devise or use some non-invasive monitoring system, just able to record and transmit a change in the traffic light status. So to know when the red is coming, when the green is coming, and so on and so forth. So this was one of the components, and then other components were installed, so the cameras, then there is on the bottom there the unit that is going to do the processing, and then we have a roadside unit up there, the antenna thing, which is going to transmit the signal if needed to the sensor on board of the car or the tram to say, okay, there is a danger coming up. And now we have some results. Okay, so this video, we are going to have Ali explaining it from the Barcelona supercomputing.
So thank you, Elisabetta. I'm Eli Karchakli from the Barcelona Supercomputing Center. And in BSC, we're responsible of implementing the data analytics and fusing together the different sources of information, which were the cameras and the traffic light manager provided by the city of Florence, and also integrating information coming from the tram. So in this specific example, we will see that we have some information coming from the NGAP module of the tram, receiving the position in real time. So in this video, we will see the result of the analytics applied in one of the cameras that we had available in Resistenza. So in this video, we monitor this intersection, and we have defined some semantic areas that are the areas of interest in order to detect some specific events. So in this example, we will focus on okay. Let's see if we can do it again. We will focus on 3 different types of events. The first one is cars crossing the part of the intersection, which is this square part here, when the traffic light is red or the tram is approaching. The second type of event that we will see is pedestrian crossing at the track part. So all this part of the tracks is an area that pedestrians shouldn't step on. So whenever a pedestrian is detected crossing this part, we generate an alert. And the third type of events is the fact of pedestrians crossing within the zebra crossings, but when the traffic light status is red. So you will see that when these specific events are captured, the boxes of the detected pedestrians or vehicle turn into red, and we generate an alert. So this alert is eventually transmitted through the vehicle-to-everything infrastructure to the connected cars. And also, this information is then transmitted to the cloud for further offline processing. So let's see the video. So you see, for example, that this truck was turned to red. The pedestrian is crossing where he shouldn't cross. And now, at some point, the traffic light has turned red, so this also generated an alert. So that's all for my part.
Thank you. So this is how it's done in practice, and just to go back and reconnect it to the scheme I was showing earlier, as Ellie said, data are going to be collected there, they're going to be processed. If there is this need to issue a warning sign, there is a roadside unit which is going to send a signal. On board of the cars or the tram, there is this onboard unit, there is a receiver, which is going then to give us some kind of warning. So for example, if there is the risk of a queue forming ahead, or if there are these pedestrians which just cross by, then we are going to get the different kind of signals here. And this was the part concerning safety, security in the real-time analysis. Now we have a second video which is going to introduce us to the concept of dashboards, which are the tools that we use for monitoring and for trying to understand the patterns, as I was telling you earlier. So Cesar is going to explain us a little bit.
Thank you very much. My name is Cesar Marin from Information Catalyst. Can we go to the video, please? And there we go. Okay, this is an example of the different presentation of the data once everything arrives at the data center. Once everything is collected from the different trams and tram stops. So we see we have the potential to generate graphs, for example, plotting the transition of traffic lights and see how they align together with the size of queues right in front of each traffic light during the day or during a period chosen by the user, or visualize the distribution of the queue size for each traffic light. Yeah? And this information can be used by traffic engineers to determine points during the day where they could do something to the infrastructure to improve the flow of people. Yeah. Part of the alerts generated that we saw in the earlier video show when people are crossing when they shouldn't. Yeah, so we can plot this information here together with other vehicles around the same time, around that area, and identify moments when we have dangerous situations. The same information can be also plotted using maps, yeah, when we can indicate, for example, queue sizes or different vehicles in that area. So the beauty of this is that as a user, you have all that information coming from the infrastructure, and you can plot it in many possible ways. And we have this separated in different dashboards, one per intersection as chosen for the project.
Thanks, Cesar. So just to give you some examples of the dashboards that we can analyze, we might have something like this, which is pretty useful for traffic engineers. This one is going to correlate the length of the queues on top with the status of the traffic lights. Of course, it's not just, okay, it's red, you have a queue forming, but there might be different kind of interactions. It might be that the red light is coming, but other traffic lights around that are going to give you the green. So the cars are coming and then they're getting stuck at the next traffic light. And all of this can help us in optimizing the synchronization of the traffic lights. So this is one, and the other for the safety aspects. Again, going back to the problem of pedestrians crossing where they're not supposed to. Well, it might be exactly because the tram is coming or it's leaving, so we have many people around and they just want to go home or want to hop on the tram, and then they're going to cross the road. Collecting data in this sense might then help us to devise a better timing also for the pedestrian crossing signs. So with this I came to the end, and what we can say is that we studied how our issues can be addressed using the fog technology, the fog architecture of the elastic setup, both to address this safety and these optimization issues in real time and in remote analysis. And we found these tools very powerful in addressing these problems and these questions. And also in paving the way for more developments in these collaborative and coordinated automated vehicles. So I think now we can just switch to the next presentation.
Okay, next presentation, please. I'm Claudio Ravaglia from Jest, and I'm presenting the maintenance, predictive maintenance use case. We focus on the track wear detection, and we installed on our maintenance vehicle that is now on Unità. And we have installed several cameras, one in the front for a panoramic video and one under the maintenance vehicle to have a visual prospect of what the measuring box, there is a laser scanner, is getting the information. On the inside, we have a central unit that is basically a PC with that do the data from the acquisition. There is also a tablet unit and a Wi-Fi unit. And there is also an end-gap equipment from the other. This is an example of a data acquisition. This is the laser blade that you can see that is scanning the rail in search of any issue. The acquisition has been done every 2 weeks on the first line. We have done more acquisition on the depot area because it's simpler, because the maintenance vehicle can only go out on night. So we can do some training on the depot area. We have installed on the depot area, we installed the full Wi-Fi coverage to automatize the data acquisition. When the maintenance vehicle come back from the truck, they can send to the Just Cloud via SFTP all the data that have been acquired. And this is the Just Cloud, and this is where the VM are stored from all the Elastic partners, and all the data are stored from the acquisition from Just. And that's all from me. I will leave to Cesar that will present a video.
Thank you. And we are moving to another video, which is about what we do once that information coming from the laser reading, what we do with that data. So we built, Information Catalyst built this software we call Predator, where we get all these readings and we let the user choose a date in that for which they would like to see what's going on. First they see this information on a map, and they can pinpoint the different readings they got on a map and see all places where the wear is within normal and safe limits, or whether the readings are actually that they would need attention of the engineers. The tool also shows the trend of those readings, whether there's been any recent change or whether there hasn't been not much change there. But also, what is of interest here is the tool is capable of predict future wear of the rail track and indicate for each side of the track whether there's been any change in the shape that would require engineers to go to that location and have an inspection. And obviously by doing that, we are helping them to schedule maintenance, which is far less costly than doing this in case of emergencies. Well, with the beauty of Google Maps, if the user wants to, they can also use the satellite view, which in many cases it's far better than just seeing this with a drawing. But in essence, yes, this is what we do with that data coming from the laser. Thank you very much. That's it.
Thank you very much. I'd like to apologize. There's a slight discrepancy between the online program and the schedule that we're running this morning. Don't disappear. We have a few minutes. So we have about 10 minutes for questions. So anybody has a question? I have plenty. So yes, please, in the back.
The object detection typical pedestrian stuff which go red. Is that any animals or living creatures or just simply people?
So the question is, when there's an object detected in red, right? Does this apply only to humans, or it could also apply to animals or objects? Who wants to take this question? Come back on stage.
Okay, so I will also, in the next presentation, we will see a bit more in detail how we perform the detection. But what we do is that we use an open source DNN, deep neural network, to detect the objects. So in our case, we use the YOLO algorithm, and we use a specific training set that was done for urban environments. So I think that the training set contains cars, trucks, pedestrians, motorbikes, and bicycles, and a few types of objects like that. So there is no specific detection for other type of creatures, animals, etc. And also sometimes the detection of pedestrians or motorbike riders and cyclists is not very precise. Now, Elastic did not focus on optimizing this detection process because we just wanted to show the capability of the Elastic software architecture to implement this type of analytics in real time. But if we wanted to optimize this process, we would do a more accurate training of the deep neural network to take into account the specific type of objects that we would like to track. So.
Thank you for the question and the answer. It's fascinating, right, to see so many use cases coming together at the end of this project. Very impressive. Yes, another question.
There's in the chat, the online event, there's a question about the algorithm's behavior under severe weather conditions.
Can you repeat the question?
How the algorithms work under weather conditions, extreme weather conditions, bad weather.
Okay, so the question is, so what is the impact on weather condition on the algorithms? Cesar.
Well, in particular for the predictive maintenance, that we have the data coming from the laser. The rail tracks, they are way too dirty, and there's rubbish there. There's grass. There's rain. There's water. It's in the end the result. It's the input data. It's very, very noisy. Yeah, so we had to apply some filters to the original data, clean to remove certain, to remove areas that were not of our interest. Yeah, and also clean in particular, if you can imagine the shape of the rail going like that. Yeah, just on this side, on these curves, that's the interest area that we were focusing on. So those were the areas that we cleaned the most during the analysis. The rest, well, we just ignore because it's just way too noisy. Does that answer the question?
Want to complete this?
Yeah, I don't know if the question applies also to the tram, but let's answer also for the tram part. So in Thales, we are really worried about this part, how the sensors deal with different weather conditions. And at the moment, we didn't do measurements with different weather conditions in the field. What we did, we implemented the simulator. We modeled how the different weather conditions can impact the functionality of the system, and so we are running synthetic experiments with different weather conditions. The next step will be to implement a real testing campaign with real weather condition tests.
Since you covered the two use cases, I will cover the third one. And I will only say that we will discuss this further in the last presentation about the non-functional requirements of the system. Because in the use case of the city of Florence, what can affect is the high temperature, for example, that may make some of the edge nodes vulnerable due to the high temperature. So we will see how the system is able to reconfigure itself up to some point and reallocate the resources based on the current conditions. So this will come this is a spoiler for what is next to come.
Thank you. I think every sensor strategy is challenged differently from different weather conditions, and this is why I think the fusing strategy that you described earlier is really interesting, because it probably increase the chance of finding gaps in the different weather conditions. So fusing things probably improves the probability of being able to remain sightful. We have time for perhaps a last question. Sure, forget it.
How big is the latency of takeoff? How autonomous is a tram with ADAS? Is there a safety guardrail?
So let's tackle so one question on latency, right? So what is the latency, the time it takes to round trips? So, is that something that we're concerned with? I think so. Do you want to?
Yeah, for the onboard decision about whether there is an obstacle in front of the tram or not, we are, it's a soft software time decision at the moment, and this decision is about 50-100 milliseconds for the alarm to happen.
Instead, for the positioning solution, we calculate the position of the tram each 10 milliseconds. So the output of the algorithm is every 10 milliseconds.
I suspect for the laser one, the real timeness was less of an issue because you do trend analysis and so on. So yeah, okay. For object detection, did you?
For object detection, as you saw in the demonstration video, we managed to process in real time around 3 frames per second, 3 to 4 frames per second. But this is more than enough to timely detect this type of events that we monitor. For example, we track the pedestrian crossing the zebra with a satisfactory resolution. What we observed was sometimes we had some delays from the other sensors that were integrated. For example, sometimes the traffic light manager system reported the change of status of the traffic light with some delay. So in our case, we couldn't do anything. We simply probably lose some events, but usually the delay was a couple of seconds. So in the end, we caught up, and maybe we could capture a pedestrian crossing with red from the first moment, but until the crossing was finalized, it was detected. So these things can be refined by specifically attacking the parts of the pipeline that introduce this sort of delays.
And for the other analytics, the predictive maintenance and also for the dashboard for the metropolitan city, because these analytics are offline and historical, well, there's no urgency here in terms of having this as soon as possible. So measurement was not done. For example, for the predictive maintenance, the vehicle, as was said earlier, the vehicle goes at night. Yeah, they travel along the line, they get the measurements, they do some work there during the line, and once it comes back, data is passed to the rest of the system. It's being processed, but this is at night. Nobody goes into the system and check what's the result. But the following day, when they come back to the office, the result is there.
So I think another observation we can make is the fact that with latency impacts different use cases we have, right? The same way as weather will impact different sensors. So there's a Cartesian product here based on the type of sensors, the type of use case we have that the system needs to come. So that's a very heterogeneous, and it's part of the challenge of putting these types of systems together. Do we have time for a very quick last one?
Well, there's several questions here.
Pick one.
I think it's an interesting one. Can this technology detect a person who has fallen on the track?
Can somebody detect somebody? Can the system falling on a track? So can the system detect somebody falling on a track? That would be great if we could, eh?
Yes, of course, because Thanks to the sensor fusion, probably, I imagine we don't have a recording of a real person falling on the trap. We can try, but anyways, we can simulate, okay? But we have 3 different sensors, and probably the radar will be a little bit in trouble in detecting the fall down person. But of course, it will detect the person when it's still standing up. And the LiDAR will detect very well the person if there is a person on the track. And also the camera will perform. So fusing all the information from the 3 sensors, we have a quite robust way of detecting objects. And this is connected also to a previous question. Even for objects that are not known by neural networks, because neural networks need a training set with labels, and labels are a finite set of classes of objects. So even in cases where we don't see the object with the camera, we have radar and camera. So we have a detection with 3 sensors, and our camera are used in a stereo setup way. So when there is an object, we can sense the object, the presence of the object, even if we don't know the class of the object, also with the stereo cameras.
I can briefly comment on the part of the analytics implementing at the city level. So there, the capability of the system is to detect and track the different objects with the different weaknesses that are introduced by detection in the tracking module. So we can capture a multitude of events if we provide the semantic annotation and coding for that. So in our case, we didn't implement a specific use case of a pedestrian remaining on the tracks for a long time, but if the pedestrian is on the track, we will get the alert of the pedestrian being where they shouldn't be. But then we can also correlate other outputs of the tracker, for example, on the distance of objects, of vehicles and pedestrians moving, so we can have more advanced analytics. For example, when a car is stopped in a specific place, it doesn't move, this can be a different sort of event. Or if a pedestrian is stopped in the middle of the track for a long time, this can also have a different impact than the pedestrian just crossing. So these depend on the use case owner, what kind of events they want to implement.
And also having those raw recordings could also be a source of further training, right, for annotation and so on. Okay, thank you very much, everybody. That was a great session, so thank you. Hope online and in the room you're happy with this. I find it fascinating. Ellie, don't go away, you're the next one. So yeah, no you can't. So now let's try to open the lid and say, how do we do this, right? So let's hear from a top-down approach what it looks like. Thank you.
Thanks, Meb. So hi again. Now we have seen how the 3 elastic use cases were implemented in the context of smart mobility. So now let's go a bit deeper into detail and talk about how we introduced a novel software architecture that was capable of developing, distributing, and efficiently executing all the necessary analytic workflows in order to implement these use cases. So as Edu presented in the beginning of the session, we have introduced a software architecture that aims to achieve a vision with 4 specific technical objectives. The first one is to facilitate the deployment and development of complex data analytics that can run over a highly heterogeneous infrastructure. Then we want to enhance the performance by distributing these complex analytics across the compute continuum. And when we say compute continuum, we mean the whole pool of computing resources that are interconnected and span from the edge to the cloud. Then we want to fulfill the non-functional properties that come from the application domain. So we want to take into account different properties. For example, in Elastic, we will consider 4 different properties for time, energy, communication, and security that may affect the distribution and execution of these analytic tasks across this continuum. And finally, we want to exploit the high capabilities of the different edge platforms which support hardware acceleration and are energy efficient in order to do these analytics and improve the performance and achieve real-time results. So with these technical objectives in mind, we have introduced a novel software architecture that consists of 4 key modules. The first module is called Distributed Data Analytics Platform, or DDAP, and is responsible for the distribution of data and ensuring that it is made available wherever needed, either by the data analytics or by the end user, for example, to visualize the output of results. The second component is our advanced orchestrator that is responsible of deploying the analytics workflow across the compute continuum and scheduling and handling its execution. The third component is a non-functional analysis, and with this we mean that we implemented a distributed monitoring tool which is capable of monitoring in real time the status of all the computing resources across the compute continuum, and as well monitor the execution of the application. So we will see later that there is a tight coupling between the output of this monitoring tool and the scheduler. And finally, we have the fog-based platforms that include and integrate a lot of software components to provide the capabilities that are needed to implement these complex workflows. So we will see in detail that we have cloud-based container as a service, we have advanced edge platforms, and we also provide all the different functionalities for telemetry, routing, etc. So we will go into more detail for each of these components in continuation. Now, we introduced the software architecture. So how can we leverage the software architecture to implement complex data analytics workflows as the one needed for the project use cases? So here we can see the value chain, how we leverage this infrastructure. So first of all, we have to develop the analytics and handle the data distribution across the compute continuum. The second step would be to deploy the data analytics across the available infrastructure, and then we continue with the execution and scheduling of the different analytics tasks. Now, at this point, there is an interaction with the distributed monitoring tool. So as the monitoring tool follows the status of all the computing and communication components across the system, it may lead us to the conclusion that we need to reconfigure the system to adapt to some change that has occurred in the compute continuum. So we have a closed loop between the reporting of the monitoring tool and the reconfiguration, the reallocation of computing and communication resources, and the rescheduling of the application. So this closed loop provides the elasticity that is needed in order to achieve the performance required by the use cases. So having seen the main idea behind the software architecture, let's take a step back and see the different workflow analytics that were developed in the project. So without going into too much detail, this is the big picture of the data analytics methods that were developed. So they can be organized in 3 different blocks. The first one are the data modules that were developed for the tram. So these have already presented for the NGAP and ADAS use case and the predictive maintenance. The second block of analytics refer to the city infrastructure use case, the city of Florence. And the third one is the final visualization of data that is handled by the distributed analytics platform. So in the remaining of this presentation, I will focus mainly on the analytics workflow that were developed and deployed for the city of Florence. So before we saw a demonstration of a video showing how the detection of the objects and events was taking place. So now we can go into more detail and see the specific methods that were implemented and resulted in this video. So this example here are a snapshot of the 2 cameras that are installed in the Resistenza intersection. So the first thing that we do is perform object detection. So as I mentioned before, we use standard object detection modules as the YOLO in order to detect the different types of objects. So for example, we have detected a car and a pedestrian. Then we perform object tracking. And by tracking, we mean that we follow the objects detected in consecutive frames. And this is very important because then we can have information on the trajectory of the objects and also information about their speed and position, both the relevant position in the photo, but also we translate it to accurate GPS position of the users, okay? Accurate with some minor error. So after tracking, we apply the duplication if needed. And by the duplication, we mean that if we have two cameras that are partially overlapping, as these purple areas drawn in this example, we need to merge the information on the detected and tracked object and remove any duplicates. Then we aggregate all this data, and then the DDAP, the Distributed Data Analytics Platform, is responsible of transferring this data whenever needed. So we leverage this information in two ways. The first one is to perform hazard detection. So we do a semantic annotation. So in this example, we define two areas of interest. The one is the square area, which is the tram crossing, the intersection between the tram line and the street. And the second is the pedestrian crossing. And we can detect different events. For example, a car crossing from this intersection or a pedestrian crossing for the zebra, for example. And then if we fuse together with additional sources of information, such as the traffic light status, we can derive alerts, specific events that are hazardous. For example, the pedestrian crossing with red, or where the tram is near. So this type of events generate alerts that are eventually transmitted to the connected cars. On the other hand, we also leverage this information to transfer it to the cloud and do some offline processing that can lead to better policies and useful conclusions that can be used by the city of Florence, for example. So these are the two paths of the information. Now, okay, this is the application pipeline, and it can be implemented in we can do it processing one frame after the other in a sequential way. However, this becomes more complex if you think about that all these analytic functions are executed on a frame-by-frame basis. So if you have a live video stream, we have to do all these functionalities for every received frame. And if we have multiple cameras, then repeat for the multiple camera frames. So in the end, the amount of analytics that need to be executed rises exponentially. So this is where the elastic software architecture comes into play, because it facilitates the development of analytics and their deployment and distribution in an efficient way and in an easy way for the programmer. So let's see a specific example taking into consideration the instantiation of this software architecture on the use cases that we consider in Elastic. So in Elastic, as we saw before, we had some cloud infrastructure provided by one of the use case providers, Jest. And we have 3 edge clusters deployed around 3 selected intersections between the tram and the public street. So we have 3 clusters, one in Batoni, in Arcipresi, and in Resistenza. And in each one of the 3 clusters, we have 3 distributed edge nodes located in different cabinets. So this is our infrastructure. In addition to that, we have distributed data sources. We have the connected tram, as we saw before. We have the city infrastructure that consisting of the cameras and the information from the traffic light managing system. And we also have the maintenance vehicle used for the predictive maintenance case. So all these data sources generate information that is then processed by this software architecture deployed in the available infrastructure. So what are the basic functionalities that we need to take care of? First, we need to develop the analytics. And for that, we will see that we leverage an open source programming framework provided by BSc that it's called COMS. So we first develop the analytics, and then we deploy the different analytics across the compute continuum. And for that, we have integrated COMS with the NUVLA service, which facilitates a lot of the deployment across the compute continuum. Then we handle the execution and scheduling of the different analytics tasks based on some scheduling policies. And the outcome of this analytics generates data that need to be distributed as needed. So we have the offline analysis through the cloud, and we have the real-time analytics that generate the alerts to be transmitted to the cars or the tram. At the same time, we have the real-time monitoring. So we monitor all the available resources, and this can lead to the rescheduling of the allocation of the different tasks across the compute continuum. So this is the big picture and the capabilities offered by the Elastic software architecture. Now, having said that, we will go into more detail to the different components of the software architecture. So in the rest of my presentation, I will focus on the workflow scheduler and discuss these three different functionalities: the development of the analytics, their deployment across the compute continuum, and their scheduling, their execution and scheduling. So let's go back to the example of a processed video we saw before. So we have here a snapshot of the processed frame, and we have a simple example of the different analytics modules that are implemented. So here we consider only object detection, tracking, and the detection of some events. So how would we develop such sort of analytic pipeline? Well, the straightforward way would be to write the sequential code of this analytic pipeline. So we define the different analytics methods. For example, we have a method for getting the frames from the camera. We have the detection method that processes these frames and returns the detected objects and their bounding boxes. Then, for each detected object, we perform tracking, and eventually we apply the semantics and we detect some events of interest. Now, what we do with the help of the open source software called COMS is that we transform the sequential code in a code that can be distributed and parallelized across the compute continuum. And the key advantage of this approach is that this parallelization and distribution comes in a way transparent to the end user. So it's relatively easy for the developer to transform this sequential piece of code to a distributable source. So what we do is that COMS provides a programming model that enables the annotation of the different tasks. So we just put, before its method definition, we put a specific annotator, and we mark the different dependencies among the tasks. So by the term dependencies, I mean that, for example, to track an object, we need the history of the tracked positions in the previous frames. So this is a dependency, and that the output of one tracker has to be the input of the next one. So by just doing this specific annotation, COMS will take care and transform this code into a task dependency graph. So it's a visual representation of the different tasks and their interdependencies. And then it will be responsible for distributing the tasks in the available resources. So, seeing here a more complete example, it will be the pipeline of the analytics for the processing of a single video frame. So here we have detection, tracking, the duplication, aggregation of data, and then hazard detection. If we go to the next frame of the same video, we do the same, but there is a dependency, for example, between the tracked objects of the first frame and the next one. But we can see here that there are some tasks, for example, the data aggregation and the event detection, that are not dependent between them. And these tasks can be parallelized. And what is the worst thing that can happen? Well, we can process the second frame completely before finalizing the processing of the first one. But this is not a problem, because for the real-time analysis, we would just get a result, an alert of a more recent event. And for the offline analysis, we don't care about the order of this information. And then if we add more cameras, we make a more complicated graph. And imagine that this is only for two frames and 2 cameras. So in a real situation, we will have a continuous video stream. The resulting graph would be much more complex. So let's see how this deployment is taken care by COMS. So COMS has a master and worker architecture. So we deploy the master, and we provide a first configuration of the available computing and communication units. So for example, here we say to COMS that we have 3 available computing resources that have these IPs, or that can be containerized or whatever. And then through an integration with the Nuvla API, this deployment of the workers is done automatically. So Nuvla is responsible of launching the necessary containers to the available resources in an automatic way. And once this is taken care of, COMS is responsible in the runtime to distribute the tasks and handle all this execution. So This is the main functionality of the COMS scheduler and how the deployment is taken care of. So to close this presentation, we have seen that we introduced a software architecture capable of handling the development, deployment, and effective execution of this complex analytics across the compute continuum. And we saw how we take care of the deployment and scheduling and how we leverage the COMS programming model to facilitate the development and distribution of such tasks in a way that is transparent to the end user and agnostic to the infrastructure. And we saw how the deployment is done in a flexible way through the integration with the Nuvla API. Now, in the next 3 presentation sessions, we will go into detail for the other 3 software components of the software architecture. So first, we will see how data management is handled across the DDAP. We will see more detail about the capabilities of the different edge computing platforms. And finally, we will see how the monitoring of the non-functional properties is implementing and what is the interplay between the outcome of the monitoring and the scheduler. So that's all for my part. Thank you.
Thanks very much, Ellie. We're perfectly on time. It's amazing. So I suggest we go for our scheduled break, and then we'll take more questions with the next session if it's okay. So 10 minutes, 1:30. No, I have waving hands in the back. 10 minutes, 20 minutes. Sorry, 20 minutes. Thank you, audience, for keeping me honest. So 20 minutes. We'll see you back in 20 minutes. Thank you. All right, so welcome back from the break. Just as a reminder, we're here for the final event of the Elastic project. My name is Marc-Élien Aubégin. I'm a CEO and co-founder at 6 Squared, and I'm your moderator this morning. It's a great pleasure. So this morning we heard about the use cases and the high-level architecture. So in this second part, we'll deep dive into some of those details. So the first session is with Anna Quereld and Cesar Marin. So we'll start with focusing on the data, if I understand well. So take it away. Thank you.
Thank you. Okay, so good morning. I'm Anna Queralt from the Barcelona Supercomputing Center, and I have here with me Cesar. We are going to explain how data is managed in the Elastic infrastructure in order to support all the use cases and all the functionalities that we have seen in the previous session this morning, both for real-time analytics and also for offline analytics that take into account all the history of events and data produced over time. The part of the Elastic software architecture that is in charge of these functionalities is the distributed data analytics platform, including different technologies that we will see, but they are Dataclay, Druid, Kafka, and also Predator. And this part of the Elastic infrastructure is in charge of managing data in the sense of bringing the data where it's needed and when it is needed in order to support the analytics and avoiding as much as possible data transfers. So we will start with an overview of all the data we have, the different data sources, how they are integrated, providing a uniform view that is able to be processed by the analytics components. Then we are going to see the different technologies that we have integrated, each one with a different role, in order to provide all these functionalities that are needed by the use cases. And finally, we will close the circle from the data to the knowledge that is generated for the users. Here we have one of the video frames that we have seen before. Here we can see how the data in the videos is translated into the concepts that we internally manage in order to support the analytics. We have, in blue, we have objects that are cars. We have other kinds of objects that are pedestrians. And also we have information about the traffic lights. The one on the top is at this moment green for the cars. There is another traffic light that is in red. And all this conforms an event snapshot, which is a set of events that are happening within a period of time and that are analyzed in order to provide valuable results. For example, the generation of alerts. In this case, the pedestrian object is highlighted in red because it is a potentially dangerous situation has been identified because is crossing the road while the traffic light is green for the cars. More precisely, this is the integrated data model that we manage. This is how we encode all this data in order to provide an integrated view that can be processed by the analytics. We have objects with their characteristics. They have a type. There can be cars, they can be trams, pedestrians, bikes, whatever. Each object has associated a set of events which define their trajectory, which is what is used to calculate the outputs of the analytics. And all the objects are represented in the same way, regardless the data source that they come from. Here we have objects coming from the cameras, as we have seen in the Florence use case. Also objects coming from the sensors and the cameras in the trams, and other objects coming from the NGAP use case, which determines the position of the tram. All of them are represented in the same way so that they can be analyzed uniformly. And in particular, the NGAP data is represented following the FIWARE format, which is a European standard that allows interoperability with different systems. This means that if eventually some other system generating data in this format can be also integrated within Elastic, and Elastic will understand the meaning of its data and will be able to process it without any changes. Then this information is combined with, with the data that comes from the traffic lights. And together with this, the alerts are generated. Each alert has a given criticality level. There are critical alerts or less critical, and these alerts are transmitted to the vehicles also following the fireware standard, which means again that any other system able to process this kind of information or any other system following the same standard will be able to consume these alerts that are generated by Elastic. So, how does it work? So here we are going to explain all the data infrastructure that supports all these analytics in Elastic. At the bottom, we have the edge level, which are the trams that are providing data to the edge level, which are the intersections, all the infrastructure that is distributed at each intersection. And here this data is combined with the data that comes from the cameras and also from the traffic lights to perform the real-time analytics and produce the alerts in real time. Then at a more global view, we have the cloud, which manages data from all the intersections and also data that is collected over time. And in this way, well, the idea of this infrastructure is to be able to take advantage of all the different devices at the different levels across the edge to cloud continuum in order to avoid unnecessary data transfers and thus produce timely responses. And well, and we also have the maintenance use case that is also incorporating this data to this global data analytics platform. Well, sorry, and the technologies that support this infrastructure are on the one hand data clay at the intersection level, supporting the Florence use case, which has part of real time and also part of historical analytics. This use case is also supported by Druid, where data arrives by means of Kafka. And finally, we have the Predator technology, and now we are going to explain all of them in a little bit more detail. So first, we have data clay, which is a distributed object store that is developed at BSc. And well, it was originally designed for high-performance computing applications, but we have now also used them in edge-to-cloud scenarios in different projects. And in particular, in this one, the role of data clay is to integrate all this data from the different sources and support the distributed analytics at the level of intersection in order to produce real-time events, and in combination with the comms distributed processing runtime. Also, another functionality of data clay within this project is to provide information to other components in Elastic. In particular, the alerts that are generated by the analytics are provided to the vehicle communication infrastructure, and also all the data gathered by data clay and the alerts generated too are communicated to the offline analytics, to the historical analytics, in order to provide more insights that are given, taking into account all the history of events that happen throughout the three intersections.
Thank you. Well, as we have seen, Dataclay essentially manages the real-time requests. Yeah? Data arrives there, any real-time request from any analytics modules goes to there. But once that analysis has been done, data then is collected at the cloud. It comes from the different tram stops and goes to the cloud and arrives at a component called Kafka. Kafka is an open source software. It's not developed by any partner in the project, but we use it to collect this information. And Kafka itself is an event streaming platform for high performance data integration, which is precisely what we're doing. And as soon as the data arrives there at the cloud, it's made available for the other components we have sitting in the cloud, which is the historical analytics. So the analytics continues, but now is no longer considered real time. Once the data it's there and it's available for the next component, which is Druid, between these two components there are some other analytics components that take information from either Kafka or Druid itself, perform some aggregations or some filtering as well. And that data is in the end deposited into Druid. Druid is a database. Again, this one is not developed by any partner in the project. It's provided by the Apache Foundation, same as Kafka. And we are using it to power our the visual tools that you have seen in the previous presentations. Yeah, and that one is indeed developed by the project. So Druid is a storage built precisely for analytics, and it's our main storage for everything that has to do with well, most of the things that are historical analytics. And because it's a time-based storage, the analytics that we do there, it's all based on when events occurred. Yeah, this allows us, gives us the flexibility to say to detect events that has happened in different locations but at the same time. Moving on. We have another component called Predator. This one is implemented by Information Catalyst, and it's also sitting in the cloud, and it's also for historical analytics, and it takes data coming from the maintenance vehicle, from the laser unit we have seen before, and it's used to analyze the current shape of the rail track and detect where on the tracks, yeah, and over time, the shape of these tracks starts to change. Yeah, this is normal usage of the rail, and the tool, well, as you have seen before, it also suggests to the users when they should do maintenance in certain locations. Yes, and well, Predator, again, it's also mainly a visualization tool that not only sees past and current status of the rail, but also future predictions. Okay, so in essence, that's the data platform we have, supporting on one side the real-time needs, and Dataclay is dealing with all those requests in real time. And at the same time, that data travels to the cloud for historical analytics. Yeah, so we're covering the whole spectrum in the compute continuum. Just final argument, just for closing the presentation. Yeah, Mark is looking at me. In the past, the metropolitan city of Florence have been classified as a smart city. Yeah, and we have seen in the first presentation that well, they incorporate a technology to get data and to provide digital services to the citizens. We have also seen that the complexity of the problem we are facing here, different elements going on the streets, on the trams, with cars and different types of objects, which in the end are mapped into data model. We're essentially using a standard as it was said before. With that format is used across the compute continuum in all the different computing units we have distributed across the tram stops, some trams, and also in the cloud, which in the end help us cover both real-time and historical analytics needs. And with this, finally, this information is presented to the traffic engineers, who then can close the loop and see, okay, things we have done, this is the result, then we can make further improvements to in general, to mobility in the city. And that's how we are helping the metropolitan city. That's it. Oops, thank you very much.
Thank you, Cesar. Thanks, Anna. We're bang on time. Amazing. So just to remind our friends online, do please continue asking questions. We'll wrap those up at the end of the session, if that's okay with you, so that we can have a conversation at the end. So thank you very much for this presentation. Now we understand a bit more how does it work. How does it work from a data perspective, right? So the next session, we'll talk about deployment. So I'd like to invite myself and Marco Gonzalez to present. We'll start with Marco. So please do continue asking questions online, and we'll pick them up at the end. Here you go, Marco.
Hello, good morning. My name is Marco Gonzalez. I am from Iker Lange Research Center, and me and Mark will explain you a bit the work that we have done with the edge computing architecture and the platform for the Elastic project. Why we need an edge platform, an edge computing architecture? In order to be able to deploy all the components, all the services, all the intelligence, all the use cases that my colleagues have explained before, we need some real devices running software that allows different functionalities and features to be running. As we can see in the left part of the slide, we are going to be focused in the bottom box, which is the FOG platform, which is the base layer of services that have been developed in the Elastic project, that offers different kind of features that allows the other components of Elastic to have deployment, to have execution, to have monitoring of the system, of the different nodes, and to be able to fulfill the different requirements of the Elastic that we are going to analyze now. First, we have to ask ourselves what does Elastic need from the FOG platform, from the FOG architecture. First, it needs an application environment in order to be able to execute the different applications, all the different intelligence, to be able to execute it directly on the hardware, on the computing nodes, on the FOG nodes, which are in the tram stop, also in the cloud, in the depot. All that nodes need to have an execution environment which allows us to execute containers, for example, Docker containers, binaries, directly binaries executed on the OS, and also all the communications needed to communicate all these applications and all these nodes, which are distributed in all Florence in these use cases, need to be communicated transparently for the user and for the applications. Also, the Elastic architecture needs remote deployment from a central node, from the cloud, needs to deploy different applications to the different FOG nodes. And we will explain that later, how we are doing it with Nubla. And last but not least, we also need the monitoring of these nodes to be able to know what is the situation, the current situation of the different nodes, the situation of what applications they are running, how are the communications, how much energy they are consuming. All that information needs to be provided to other components in the Elastic architecture. So in this part, in the fog computing, we have different monitoring in order to provide that metrics to the platform. As you can see in this slide, this is the Elastic fog architecture that we have developed in the project. This is a generic software architecture that we have developed and is compatible for all Docker-compatible OSs like Windows, Linux, Mac. And here you can see, I will describe it a bit from bottom to up, from down to up, the different components that the software architecture fog has. First, we have the fog manager, which is the software component which controls the fog node and also makes the monitoring of the different the situation of the node, the current node. Then we have the security component. We makes an assessment on real time about the security situation of the node. We have the sensor manager, which controls the input-output of sensors, for example, reading data from the trams, reading data from different sensors. We have a component for that. Also the local storage, which is both data clay that my colleagues explained before, and also local storage that can be stored directly on the node. And then on the top part, we can see on the left all the used applications, which are the applications that can be deployed remotely to the node. For example, it can be an analytics application. And in the right part, we can see all the communications components of the node. With these components, we have an abstraction to be able to communicate between services, between nodes, and also with the cloud. So we have an abstraction to provide an easy way for the developer to communicate with other components, other nodes of the Elastic architecture. This is a generic software architecture, but then the implementation in the real nodes is done via two different implementations, which are both following the same Elastic fog architecture, but one is the Nubla box from SIG, and another one is the Ikerlan Connect box from Ikerlan. Both offer the same features, but are two different kind of implementations that we will explain a bit later. Here is just a recap. You can see all the developments that we have done, the different components. I will not explain one by one, but just as a recap of all the work that we have done in the fog architecture for Elastic. And what we are going to do is we are going to focus in the three main features that Elastic needs from the fog nodes, which is execution environment, deployment, and monitoring. We will explain a bit which are the capabilities of these Elastic fog nodes and what is possible to do with Elastic. Please, Mark.
Thank you. So here the idea is just to reinforce what you just said is in order for the stories the use cases to be implemented, we need to make sure that we have the right software deployed at the right place at the right time with the right versions, right? It's a simple problem to state. It's not that easy to actually execute, and that's why those software infrastructures are in place. So the first one is Nubla.io, which is an edge management platform. I'll show you a few screenshots a little later if you wanna see this in action. But the foundation of at least the way we do this is to deploy containerized applications, and that containerization provides us with an abstraction that is convenient to deploy to many places across the continuum. And second is to base communication based on MQTT. That's another key component that facilitates data transfer And that's what we were discussing a bit earlier. So those foundations are helpful to be able to play across the continuum. The next one is the fact that this container architecture allows us to create applications that are composed of microservices. That's another good architectural guideline, if you want, when creating applications, because we can create modular system. And using the container ecosystem also allows us to do clustering, right? So that we can actually cluster. We've done that for a long time in the cloud. Now we're able to actually move this to the edge, where we can actually have edge devices that collaborate with each other using clustering strategies. And ultimately, at the end, what we want is be able to provide the intelligence at the very top with insightful measurements that we can actually gather from across the continuum. And that's another key element to when we deploy applications, deploy algorithms and so on, we also deploy a microenvironment, if you want, that will be responsible for collecting metrics to monitor basically what's happening at the different levels and aggregate all this information so we can actually, better optimize going forward.
Okay, thank you. Then for the monitoring capabilities of the nodes, in order to provide Elastic with the metrics of the different metrics that we want to collect from the system, we have 4 different agents for monitoring in the nodes. One is for communication, another is for time, other is for energy, and the last one is for security. From the communications part, because normally the nodes have different communication interfaces. For example, the nodes we are using in Elastic have Wi-Fi, Ethernet, and also LTE connection, 4G connection. So in order to have a good view of the current situation of the node, we have to calculate the latencies between the different nodes in order to have the current status of the system, of the communication system, in order to select which communications we want to use. For example, if right now we have problems with the coverage of 4G, we can switch to Wi-Fi in order to have better quality of service. So if we do a real-time analysis of this communication status via the throughput normally and the latencies, then we can select which nodes should execute, for example, real-time applications and which not. From the time and energy part, we can monitor both the power consumption of the nodes in order to, if we want to optimize the consumption and reduce the consumption of power of the different nodes, we have the current power consumption and also the CPU load. With this CPU load, we can assign new resources, new applications to the computing nodes that are with a less load. And last, in the security part, we have an agent-based security monitoring, which is doing in real time, is analyzing the different binaries, the different applications that are installed in the OS. This agent is checking if the binaries have some vulnerabilities, if the packages are not up to date. Also, the agent can detect if someone is trying to get inside our node via SSH or via another ways. Also, for critical files of the system, the agent does automatically a fingerprinting of the files to check if someone that we don't want is changing the files. And with all this monitoring, we can check if the system is secure or not and inform the Elastic architecture with the real-time status of the security situation of all the nodes of our architecture. On the third feature that the fog computing architecture needs to provide to Elastic, we have the execution part. In the execution part, we need that execution environment for all the applications, Elastic applications, analytics applications that are going to be deployed and executed on the nodes. We need this environment that provides us with a base services of, for example, communication. What kind of communications? When we have different applications running in the node, they need to communicate between each other. For that, we have a local router that allows us, very easy for the developer, to communicate between different applications which are running in the same node. Also, in order to communicate with local sensors, for example, with the tram, some sensor that is in the tram, we have that same data router that allows us to communicate with local sensors. And the same for the cloud. If we want to communicate with the cloud or with other nodes, we have two clients. In order to send data, real-time data, we use MQTT, and bulk data, we are using FTP. In order to send this data that we're analyzing or storing in the node, send it to another node or send it to the cloud. For this, we are using the firewall model that our colleagues explained in the previous presentation. And also, we have an integration with the V2X infrastructure that is located in the different Florence tram stops and infrastructure. Next, I will explain you, as I said before, this elastic software architecture is a generic architecture, but then the implementation is done in two different products. One of them is the Ikerlan Connect box, another one is the 6 Nubla box and Nubla.io that my colleague is going to explain. First, the Ikerlan Connect box is an industry-oriented fog platform that we developed at Ikerlan, and is suited for our clients in order to speed up the development of fog applications, fog environments. It's microservices based, so it's compatible with both Linux and Windows. And we decided to have an approach based only in MQTTs, which can be connected to a private cloud or also to AWS, in order to control all the nodes via this MQTT interface, in order to reduce the exposure of the node to other protocols or to open other ports, etc. With this communication with the cloud, we are able to deploy both applications via microservices and also AI models. We are able to update in real time AI models which are retrained continuously on the cloud. And then to have multiple services like local persistent, data buffering, and also industrial protocol connectors like OPC UA, etc. For the sixth part, Mark will explain you.
All right, thanks, Marco. So that second implementation of the reference architecture of Elastic, we have Nubla.io and Nubla.box that are working together. So here's a little, like, really high-level view over the problem I was describing before, right? Is to how do you make sure that the right software is deployed at the right place at the right time with the right version and updated over time. So that's where, you know, in our case, we don't have that many edge devices on board, but that's just an illustration of it. But it's to show that that kind of technology allows you to have an overall view, so that from a single deployment platform, you can actually, you know, position and, you know, place the right apps or the right algorithms at the right place, whether it's at the edge, in the cloud, or in between. So that these are, you know, the two pieces of software working together. Nubla.box is open source, and the idea is that you install it and it turns any Linux-based system into a connected edge device, so that it becomes remotely controlled from Nubla.io. And Nubla.io is the management platform that gives you this overview over the system. In order to actually deliver the value that I'm describing, this is what we need, you know, from an architecture standpoint. I'd rather not go through the details of all those components, but show you something a bit more visual, which is a bit more, I think, interesting. But this is the type of if you open the lid on the service, these are the components that are required to deploy, and that's what makes it compliant with the Elastic architecture. Now that was for Nuvla.io, right, the management platform. If you dive into the Nuvla box software stack, that's what you have here. And the common theme that comes back, is this, I've enlarged here because it wasn't visible on the original image, is the data gateway. So that's the MQTT bus that we have inside of every edge device that provides a mean of communication between the different applications on board, but also the way it's going to communicate with upstream information if it talks directly through that protocol. And that architecture was really enhanced and hardened through the project. So what does it look like if we just have if you look on the Nuvla.io user interface? That's the dashboard. I don't have a laser, but you see I'm switched to a group called Elastic Flow. Okay, so that's the project that actually oversees the group that sees all the resources that are relevant for this project out there. So we have 10 edge devices, and actually there's 12 applications. When this one was taken, there was 9 started. 1 was in the process of being started and 2 were stopped. Okay, so it gives you like a view over what application is deployed where. So if we dive in to the edge devices, then we have the ability to geolocate. Now, all of them are in Florence, but you can imagine when you have a more geographically distributed application, then it's really helpful to figure out where's what in terms of monitoring, right, and health of the application that are deployed. If you zoom in, then you can also have the individual health and details of each card represents an edge device, and that gives you this visual feedback over what's going on. Now, I'm showing you this for you to understand the integration in the operational model of Elastic is done through the API, right? Behind this user interface, there's an API. That's a single page app. But behind there's this API that is used by comms, for example, to create the initial deployment and manage all of that. We were talking about monitoring, right? Telemetry gets reported, and this is a visual representation of some of that telemetry. So it gives you the details of what's happening from those different individual edge devices, and that's part of the information that is used to do the work of assessing whether an edge device is healthy and if it's able to actually run the applications that it's intended to. If you switch on the application view, then we have a bunch of applications that can be deployed easily through the user interface or through an API call, and that will guarantee will do everything it can to actually deliver that application at the right place in our edge to cloud continuum. I couldn't resist to put the cat here. I think it's cool. But it's an object detection application that we use a lot in demonstrations. But basically, there's a lot of data clay-based application because these are some of the nodes in terms of application that being deployed at the edge. And this is a view over the running application. So I mentioned 12 applications earlier. This is a view over those applications running out there, and they're all attached to a specific edge device, so we understand where all of those applications running. I think that's it for us. Well done, Marco. I'll jump to my next different hat. Again, thank you, Marco. So before the Q&A session, we have one last presentation. So Luis Miguel Pino and Ellie, I think you're required again on the stage to talk about elasticity in the edge cloud compute continuum. Take it away.
Thank you. Okay. So you sit down, like you. Okay. So so the goal of this presentation is to showcase how elasticity comes together in the architecture in the project. If this works. No, okay. So recapping a little bit, so we have been hearing a lot about the importance of extreme scale analytics and the need to fulfill the requirements which are posed by those applications. A lot about them is on data in motion analysis, on how we can process these data streams in the fly in the project. And before going that, I think it's important that we look a little bit about the requirements, the non-functional requirements that we also need to address in the project. So one of the goals of the project was to be able to provide the amount of resources needed to the applications, so no over-provisioning or under-provisioning, but fulfilling some requirements related to time, energy, communication, quality, and security. So starting with those, the idea is that for these type of applications, so not restricting to the use case of the project, but to smart applications in general, we need to guarantee that some requirements like response times or predictability in the time domain, energy efficiency, because for instance for mobile devices this could be a huge requirement, but also communication quality between the nodes in the system, and finally security, that these properties are maintained by the Elastic system even when changing the configuration, even when adapting to change of loads or situations. So in this process, one of the challenges is the fact that there's a lot of interdependency between those requirements. So for instance, if you move the processing to the cloud to get a higher processing capabilities, then you are challenging your communication quality of service. Even time and energy, so if you speed up your processing, if you give more computing power to your processing to achieve a faster response time, then you will have a higher energy consumption on your mobile devices. So there's an interplay in those properties that needs also to be addressed. So before going into how we address them, let's discuss how in our Elastic we looked at those non-functional requirements. So we started by analyzing the requirements from the use cases and similar domains from those 4 dimensions. So we ended up having a set of 67 requirements that we had to tick. I will not go through any of them. But just to give a small summary, so for time, the main factor was response time, processing, the processing time, the fastest response time, but with predictability. For energy, in the Elastic use cases, the requirements were not so demanding, although in the smart domain for mobile edge devices, we actually need to allot the energy efficiency at the nodes. In terms of communication quality, obviously the QoS of the communications were a very, very important factor, like Marco already presented. And finally, in terms of security, things like authentication, encryption, but also privacy was one of the requirements that was raised by this analysis. From that analysis, we ended up determining that Elastic would need to provide mechanisms which allowed us to specify the level of non-functional properties that we need to meet, mechanisms in order to analyze those and determine configuration of the system, and then the approaches to monitor the online execution of the applications and reconfigure if needed to fulfill the requirements. This leads us to the development of what we call the NFR tool, which is a component of the Elastic architecture that monitors those requirements and provides the adaptation requirement in terms of system configuration. So going back to a picture that we have already seen, that Ali presented in the previous session. So this is the software architecture and the flow of Elastic. So we are going to present the NFR tool, which is the box on the left, and the flow, the final part, the loop, the execution, monitoring, and reconfiguration loop on the online execution of the project. So going to the software architecture, as I noted, we developed the NFR tool, which has several components, but from a high-level perspective, it provides basically the capability to monitor the properties on the different dimensions, then analyzing the eventual problems in those dimensions and determining what reconfiguration needs to be done in the system and specifying this to the orchestrator that Ellie already presented, which then actually makes the rescheduling of the applications in the system. In terms of the implementation, so basically what we have is a set of conceptual probes which are executing or are available in the edge platforms that was presented by Mark-Elik and Marco. And these are, the information on these probes is provided to resource-specific monitors which will identify the issues, the violations as we call it, of non-functional requirements in order to provide the global resource management with the information needed for the reconfiguration. So all of this is transmitted through MQTT. Basically, it's a publish subscribe of the information, but the configuration, the changes on the configuration and the metrics, they are also stored in the distributed storage provided by DataClay. So DataClay is also used not only for the applications, but also for the internal configuration of the Elastic system itself. To see how it is actually deployed, so these are some pictures from one of the tram stops in Florence, so Battoni, and here we can see there are two Elastic cabinets installed there, and in those cabinets we have actually 3 Elastic nodes executing. These 3 Elastic nodes, so we have one NFR monitor, so the components that do the monitoring of the resources in the system. They are distributed in those nodes, and the global resource management is only per cluster, one per cluster, which is actually managing the resources on that cluster. Now going into the details of these components. So for time and energy, as Marco presented, we have CPU load and power consumption in the nodes. This is what we are monitoring. Then we have specific thresholds which are extracted from the actual execution of the applications in the system, and these thresholds are used to compare the values that are being recorded, and if there is a problem, so a violation is sent to the resource manager. A similar approach is used for the communication quality, where the metrics is the quality in the links of the node, and again, if thresholds, in this case, thresholds of lower quality are attained, then also violations are informed to the global resource manager. Such as in time and energy, communication quality, also these metrics are all stored in DataClay. Finally, for security, as also already presented, there's a monitoring being performed, but in this case, there is a small difference in terms of the behavior, in terms of a violation, because in this case, a security violation implies not a rescheduling, but actually that node can no longer be used for applications requiring security. So to see how this is done then in the resource manager, I'm going back to an example that Ellie already showed in a previous presentation. So basically the initial configuration, we have the different master and workers in the edge devices, which have a specific number of CPUs or computation units, for instance, attributed to each node and to each worker. And then what happens is if there is a violation, if some worker is actually experiencing a higher workload in that node, we may say, okay, then we need to reduce the CPU load in that node, which basically means that eventually this node, even the worker can be deactivated, and some other worker needs to be deactivated, and the computation load is shifted elsewhere. So I will leave to Ellie to present now on how the orchestration component actually puts all of this together and actually does the rescheduling.
Thank you, Miguel. It was a great presentation. So I'll just have a few slides explaining an example of how this rescheduling takes place, taking into account the recommendation and metrics provided by the NFR tool. So going back to our previous example, remember that we have the different data analytic methods that were described by a task graph. So in this example, we just have 2 consecutive frames being processed. So having the 3 available edge resources, the COM scheduler, based on some scheduling policy, will determine how to deploy and schedule these different tasks. So let's consider this specific example. This would be the processing of 2 video frames obtained by 2 cameras, and that the next video frames would also be distributed. So the scheduler makes this task allocation in periodic intervals. So these are the scheduling intervals. So in this example, we have a scheduling intervals of 2 time frames per camera. So for this scheduling interval, and if we consider this specific allocation, we can determine the overall workflow response time, what is the time needed from the start of the execution of this workflow up to the final completion of the last analytics process. So the scheduler can implement different policies, all aiming to minimize this workflow response time. Now let's see how the NFR tool and the GRM come into play. So what happens is that in the 3 edge devices, we have the NFR tool monitoring, continuously checking the status of both the application execution and the performance of the edge computing devices. So based on the different thresholds that have been defined, the NFR tool is capable of detecting violation to these thresholds. And these violations are reported to a centralized entity that is the GRM. So then the GRM can take some actions and recommend some actions to the comms orchestrator, which is the one that will eventually implement these policies. So we have different levels of rescheduling. We have coarse grain rescheduling, that is either turn off or turn on a worker on a given edge device. And we also have fine grain scheduling that, as Miguel said, we can alter the number of allocated computing units for the execution of the analytics. So let's see a more complete example. Going back to the same figure where the 3 deployed workers in the edge devices, let's consider an initial allocation of our workflow. So let's assume that this is operating in a stable way, and at some point we note a violation, maybe for the time and energy component. Let's say that due to extreme weather conditions, it's very hot and the temperature of the CPU is rising a lot. So the GRM will issue a recommendation, and probably one possible action will be to, let's try to reduce the computing units used in this compromised node to see if the performance improves. So comms will be alerted of this reduction of available computing units, and one potential action of the scheduler could be like, since I have less computing units in this edge node, I will allocate some task to a different node with more available computing power. So we can have like an example of taking one task and migrating to a different computing unit with better resources. Another example would be for the GRM to turn down a specific worker. This can occur due to different reasons. The most straightforward reason would be for a security violation that compromises this node. So the action would be that for our secure application, this node must not be used. A different event that can result to the same outcome would be, for example, continuously having violations of the time and energy component that keep reducing the computing units until the node has to be turned off. Or not turned off, but not used. Another possibility would be for the wireless link, for example, to be turned off or to be for some time disabled due to an obstacle standing in between the line of sight. So this would the result for COMS would be the same. COMS scheduler would know that this specific computing unit, computing resource could not be used. And the result would be to reschedule the tasks that are currently running in this compromised node to a different and more suitable resource. Now the third part of this example would be what happens if a compromised node is recovered. Let's say that the security issues are being fixed or the wireless link is, again, has a high quality. So what happens is that the NFR tool continuously monitors these nodes even if they are compromised or disabled, if possible. And if the operation is recovered during a given period of time, COMS is alerted and is able to reutilize these resources. For example, some resources can go back and be rescheduled to this worker that was previously disabled. So wrapping up this presentation, I would like to say that another feature that we don't present in this example but is very important is to understand that the integration between the GRM and the NFR tool with COMS has two components. It has a distributed operation but also a decentralized component. So some metrics are obtained by the COMS scheduler in a distributed way. For example, the computing units and the quality of the communication link can be consulted in a distributed way to do the scheduling. So the COMS can know at any time that the specific links between two workers has a specific quality. But then there is scheduling that need to be done in a centralized way. For example, if we have two different applications sharing the same resources, then this view cannot be obtained by the COMS scheduler. This view has to come from the GRM component, which can see the different priorities of the two different applications and can allocate resources based on the priority of the applications and the requirements. So I think that's all from my part. I don't know if you would like to. Okay, so thank you very much.
Great, thank you very much. So with this concludes the second part of our event. So thanks very much for explaining what the last piece of the puzzle with respect to the non-functional requirement part. We now have 35 minutes for Q&A. Right, so please, I think so. Thanks for the presentation. Thank you. So we already have a number of questions that have been asked online, and there's a few hands in the room as well. So Edu, you want to help with pulling out some of the questions from and then we'll probably ask for our experts back on stage to answer some of those.
Yes. So in fact, I'm going to ask all the people that has presented to come here, because this is not the work that has been done by each of us, but has been worked by all of us. So could you come here? Miguel, Eli, Marco, come here. Cesar, Anna. Okay, very good. Thank you. Okay, okay. So there have been a number of questions. So some of those I think has been already addressed during a presentation, but I think it's good that we can enforce these questions again. So the first one is, are you improve your algorithm on the severe weather conditions? And this is probably a question for Vincenzo.
Yeah, I believe we answered already after the presentation. Anyways, we are not doing measurements of weather conditions on the field at this stage. What we did was to create a simulation environment where we can inject noise on different sensors, on radar, camera, and LiDAR, so that we can simulate the effect of weather conditions on different sensors. And of course, it is expected that the weather conditions will affect our system, and so we will have to take it into consideration. What is a possibility for us is to leverage the fact that we are using different technologies, so different kind of sensors. So a weather condition that can badly affect one kind of sensor is not affecting the other one, and vice versa. So in the real world, probably the real situation will be better than what we are simulating now.
Okay, so thank you. So the second one that was already addressed by Ellie is how big is a latency on a data use in the real time for the collision detection. So here I think we have two parts. I would say one is the collision detector that is implemented in a tram, and there the latency, the communication latency is much smaller than, for example, the use case we are implemented in a city, in which there is a distribution on the computation, as Ellie has already presented. But we can roughly say that we are, in the case of the smart city use case, we are in the range of 10 frames per second, which, taking into account the speed at which the event occurs, it's far. And for the tram, I guess the speed is the frames per second able to be processed is much higher than this one.
Yes, for the camera, we have optimized we as well are using the YOLO implementation, but we optimized a little bit on ourselves, and we changed the head of the model to make it more lightweight. So we are running at about 20-30 frames per second on the camera. Of course, this is not the frame rate of the system, because we have much more information than this, because we have also radar frame, LiDAR frame, so all the sensors cooperate together. So the number of messages we get from sensors per second is distributed unevenly at about 70 times per second. So it's a lot of messages.
Okay, so thank you. Then there is also a question that it's how autonomous is the tram with the ADAS? Well, the tram, just to make it clear, is not autonomous. In fact, the name of what we claim is we are implemented towards autonomy, and so there is always either there. In fact, these are trams that are in regular operation. This means that are trams that are bringing passengers. So there is no real autonomy. Then there is another question that says, how do you detect the traffic lights? Okay, so this is something that has been addressed by several presentations, but I can answer this. So the idea here is that we are reading from the state of the city directly, for the system in the city that is controlling the state of semaphores. So this allows us to have access to the full networks of traffic lights of orange. So it's not that we are reading one single traffic light, but we can read all traffic lights that for the use cases, of course, we are only interested on those in the 3 tram stops, but we can access to any of those, which I think it's one of the positive things about the elastic technology is that we are able to gather all the information, not from the cameras only, but from the information that the city is collecting. Then there is also a question that is, did you use your own cloud or use a third-party cloud? So perhaps, Mep, you can answer this question.
Sure, thanks. So I think the architecture, we have to actually state that the reference architecture of Elastic is cloud neutral, right? That's important. Otherwise, it would really constrain or restrict its applicability. Now, in the reality of the implementation, we've used a private cloud from Jest that was mentioned several times. When the tram goes back and then data is offloaded, or that's where a lot of the top level, high level functions are running. But the architecture itself is cloud neutral, and let me just emphasize, when I say cloud, it really is public, private, hybrid, right? It would work in all of those cases, and from our perspective, from a Nuvla perspective, we do support all of those flavors of cloud. So when we say we've tackled the continuum, from I think the things to the cloud, right, beyond edge, and edge is of course in the middle. I think we can sustain that claim in a very generic way, which I think is quite powerful with respect to our architecture.
Thank you. Okay, the next question is how will Elastic deal with cyber threats to a smart metropolitan city? So, Arco, you want to answer?
Okay, about cybersecurity threats, because we are doing a real-time assessment and analysis of the security of the different nodes, where we are assuring is that all the critical applications that need security will be only deployed in nodes which are secure. So it's impossible for a critical application to be deployed in an insecure node. And we can define the different thresholds for the security in order to be more strict or less strict for each one of the nodes. So, for example, nodes which are accessible from the outside, for example, which are in a tram stop that someone can access physically, we can put in a strict threshold, a stricter threshold, in order to assure that the cybersecurity of the system is always at least controlled. Controlling the set of rules. It's impossible to have a complete assurance of the cybersecurity, but we have a very high percentage of occurrence that if a node has some vulnerability or someone is trying to attack it, at least we can disable it as soon as possible, remove all the critical application and all the critical data, and just disable that node for further exploration and analysis afterwards.
Sure, absolutely.
Yeah, I just want to add, because we in Thales care a lot about cybersecurity. Of course, we are one of the leaders in the sector. And so for the components that are on the tram itself, so ADAS and GAP, they are on the process, as Gianluca said, to become a Thales product. So because of this, they have been designed with cybersecurity by design and cybersecurity by default, complying to the ISA EEC 62443 standard at security level 2. So this is very strict requirement from Thales, because this is our baseline cybersecurity level.
Just to complement, I mean, there's the threat, right, that tends to come from the outside. But when we're looking at a complex system like the one that has been demonstrated today, we also need to recognize the need for governance, right? Because if we don't have high control at the governance level, we might end up having internal threats, right? Something that slips in, right? And that's where something that we've been working on as part of all of the beauties of these types of projects, we observe, right? And we we think about what are the Gedanken experiment, well, what if this and that, and how do we handle this, and so on. So one of them was really to focus on provenance. Okay, so we're able now, in the Nubla box software, to ensure that a device will only accept Docker images that are coming from a known source, and even signed by a known authority. Right? So the idea is really to put it in the context, to put cybersecurity in the governance context, to ensure that whatever is running across the continuum, right, is actually of good signature, right? We understand what it is. So to basically push back potential inner threats that might come as well, to simplify a little bit the problem domain. So that's another way to maybe answer or tackle that question is, make sure you defend your outer borders, but make sure there's no back doors that might slip in.
Good, thank you. Okay, so the last questions from the online audience is, what is the maximum recovery time for a compromised node? Or what is the longest time a node could be disabled? So perhaps you want to answer me?
Okay, so answering from the last, the maximum time a node could be disabled, well, if the node has some serious issue, it may be disabled permanently. So, but the issue is that all of this is configurable, and it is configured from analysis of the system. So basically, we have several times, let's call it like that. So we are checking the metrics in the system. If I'm not wrong, it's per second information that we are receiving. So we are then saving these metrics in DataClay, for instance, for each 5 seconds. But the reaction to the events is not periodic; it's reactive. And then after we have a problem in one of the nodes, we have what we call it the instability time. And this is the time that we consider, okay, the node is unstable, let's do the change and wait until the end of this instability time to see if the issues have been solved and we don't need to act further. This instability time is extracted from analyzing and executing the system, and I think that currently is set up in the setup that's there. It's 30 seconds. And then we have what we call the stability time, which is the time that the node needs to be without any problem before we start putting this node back on the system, or increasing computational units, or actually activating the node if it was deactivated. It's also depending from the analysis, and I think that currently it's set up as 120 seconds. So 2 minutes. But the idea is that the more data that we have from actual execution, these values will be tuned in order to better reflect the actual execution of the system. So I think it's similar to other parts of the project that as more data is available, we can actually reason more on how to deploy and execute the system. And I think Ellie wanted to add something about the scheduling itself.
Yes, I would like to add that on the one hand, if a node is disabled due to force, if it turns off, the scheduler will notice immediately because the task will not be executed. But if it is a scheduling decision recommended by the GRM, it will be taken into account in the next scheduling cycle. So the delay will be different depending on the kind of source of this deactivation. If the GRM just recommended not using this worker for some time because of a time and energy violation, then the scheduler will simply not use this available worker, not schedule any tasks, and then when the GRM recommends again to use it, in the next scheduling cycle, immediately the task will be allocated and executed. However, if the node is shut down and or the worker is permanently turned off, recovering the system will take a bit more time because we have to redeploy a worker, so this will be done through Nubla. So it will take some time, depending also on the wireless connectivity, to migrate, redeploy a new worker, and then schedule some tasks there. So.
Just, I mean, just to reflect a bit on, past experience. Removing a resource is the first thing to do when something goes wrong. It's probably the easiest thing to do as well. Bringing it back, that's more tricky, right? You need to align many things in order for, suddenly you're moving the landing strip, right? So, whoa, no, where am I landing my airplane now? And that requires, finer coordination between the different components. And I think we've done that. I think, and that's something we should, celebrate this, because it's not that trivial to bring back a resource, especially, depending on its pedigree, where it was when it was pulled back. When you bring it back, then you need to resync a number of services in order for that resource to be sound, right? To behave as it was before it started to misbehave. So I think that's another great, result of the project is our ability to coordinate, a number of complex processes, not only to remove a threat, but then when the thing is sound, you bring it back. Because remember, in production, these environments will run for years, right? So it's easy to pull things out, and if it's difficult to put them back in, then at one point you always, like, gravity is going to start pulling you down over time, which is not a good thing, right? So just to say, well done, guys.
Okay, so I would like to complement this because this, I think, it's an important message. And this is one thing that Miguel has said already, but I want to reinforce this message. So we have provided tools to do this. We are not tied to any scheduler. We are not tied to any specific number of seconds of recovery. This is fully configurable. So in that respect, I think that Elastic is also providing an excellent tool for the research community in order to keep working on how to distribute these complex systems in a fully heterogeneous environment. Okay, so with this we finish the online questions. So I don't know if there is a question from the audience. Okay, okay, you have one. You have one. You are not allowed. You are not allowed. Okay.
If you don't mind, I think this is a great opportunity to actually just reflect a little bit on challenges, because it's great to celebrate success, which I think we're entitled to do today, but it's not straightforward, right? So maybe a question I'm interested to at least have element of answers is, what are the challenges, right? What are the things that are difficult, and that we started that journey a while ago, and then that led to where we are now.
Okay, I will pick this challenge. I mean, one of the things that I think is the next step is we are always considering that we have full control, or up to a certain extent we have certain control of the edge devices, because it's something that we own. Well, the city of Florence, the città metropolitana di Firenze owns. So we have access to it, we can control it, but it is not going to be like this in the future. And in fact, UBLA is providing means to have access to remote devices in which you don't have such a control. But to me, the next step is a multi-tenant edge system in which there is a device that is going to be entered like we do today with the cloud. And then the number of challenges increase a lot, because you are not going to execute one workflow, one tenant, but you are going to execute multiple tenants from different agents, from different actors, from different companies. And there, the challenge is the real-time challenges, security challenges, privacy challenges are going to be huge. So I don't know if you want to say something about the challenge that our colleague has provided. Of course.
I just want to say that from the perspective of a use case partner of the project, yes, of course, there were challenges like in all the projects that you can take part of, because something unexpected can happen. In this case, probably somebody was talking about pandemic, so it was a little bit delayed. The infrastructure, we had some, so we did very good progress even during the pandemic. And one particular point that is the opposite of the question, so it's a good point of that, is that for us, really, many of the things were transparent. Nuvla, Data Clay, or the technology that we interacted with were well suited for the task. So for us, a good point is that, yeah, there were not so many challenges in interacting with this technology, even with the pandemic.
Okay, good. So I think with this, we finish the questions and answers session. And so let's go to the final 2 slides. And I'm going to ask you to stay here, okay? So I have only 2 remaining slides. The first one is the home taking message. Well, there are many, okay? So it is not that you have to take 2. I mean, you can take as much as you like. But at least there are 2 that I think are important to emphasize. I mean, all the things that we have been explaining to you can be summarized in perhaps these 2 bullets. So the first is about the importance of having this software architecture, okay? It is not that, let's say, we have invented a completely new architecture, but it's like we have picked the right components and we have put all them together in a smart way. So then we have tried to achieve one of the 3 points that I think are important, that is to increase the productivity, the software development productivity of complex data analytics workflows being deployed in such a distributed environment. That this is a strong need that is needed in the smart cities. The second point is that because we are increasing this productivity, we can focus on enhancing the data analytics and not concentrate our efforts on how to run this under the infrastructure, because this is already provided. And not only this, we can take the benefit of the different characteristics. We can take benefit of the edge, we can take benefit of the cloud to run different analytics. And the last point is that this is, I think, one of the key innovations that in this project we have been working on is a fundamental property is the need of fulfilling the non-functional requirements like real-time energy, privacy, security, etc., etc. And we have used these technologies in order to implement three innovative, challenging, but still realistic use cases that I think are taking all the potentiality of the software architecture. And my last slide is just to say thank you to all, including myself. So it's to us, okay? Because there have been, there have been difficult, to make the project advance during the pandemic time, I mean, the first time we had access again to the infrastructure was 3 months ago. So, and it's not the same at all. You know, working remotely, I mean, the Cheetah, Orange has provided all the support in order to facilitate this remote access, but it's not easy at all. And that's it. Only thank you guys. And I think with this finishes this session. Thank you very much. Thank you.